The Compose hot reload implementation, aka Project Firework, will soon be promoted to alpha. It was shown in the previous video that implementing hot reload with class loaders has too many issues to be practical. But how else did we implement something as powerful as this? You can see here in this example with the click me counter, us adding a new function that will render this counter even with an animation. We will replace the current existing code by calling into this new widget instead of directly rendering the counter. To summarize, Compose hot reload allows you to add new functions, remove functions, change the signature of functions, add classes, remove classes, add properties to existing classes, remove properties to existing classes, and even add supertypes. Although removing supertypes from a class is one of the limitations. And all that is required as a user is applying a Gradle plugin and for now using the development entry point wrapper function. This development entry point shall be used after creating a window. Before we get into details about the star of the show called DCEVM, providing a short overview of the components at play here might be a good idea. Let's think about it from a high-level point of view and collect what we can come up with. The app, which we would like to work on, and hot reload needs to be launched. Therefore, we need to compile the code initially, collect all runtime dependencies, and set up the JVM to properly launch our code. This requires the integration of a build tool like Gradle or Amper. Once the application is running, we need some way of recompiling the changed sources. Classically, the IDE does this, and it has a suitable compiler built in and set up ready to go. However, the current prototype also uses the underlying build tool to recompile, not the IDE. This leads to a more predictable experience and should improve the trust in the development process. The IDE recompilation might be fast, but being burned once by trying to debug just to find out that the code you thought is running was not actually running is quite an unpleasant experience. It is just very hard to replicate the exact compiler invocation of a complex build from within the IDE. This predictability comes with an unpleasant cost though. If your Gradle build is slow, your recompile will be slow. If your Gradle build is fast, your recompile will be fast. It is highly recommended to enable Gradle's configuration cache and ensuring your build is not doing some unnecessary work. Next, whoever is recompiling the code needs some way of communicating with the JVM currently executing our app, informing it about the changed classes. This is called the Orchestration server. Similar to a debug server, this can be hosted by the currently running application using a Java agent. Okay, so we launched the application which hosts said orchestration server. The build tool informs it about the changed classes. How in the world are we able to freely reload the classes on the JVM without using class loaders? The answer is the star of the show, and it is supported only by the JetBrains runtime. It's called DCEVM, Dynamic Code Evolution for Java, which was proposed by Thomas Wittinger, Christian Wimmer, and Lukas Stadler back in 2011. I highly recommend reading the paper, the link is in the description. We can get some basic understanding of the DCEVM first, before we look into how to use it. Let's consider an application with two classes, foo and bar, where foo has a property x. When adding another property y to foo, recompiling and defining it, the JetBrains runtime will load the new version of foo alongside all other classes and builds what is called a side universe. The old version of the classes will still be available as there might still be old code actively executed. Once the runtime verifies the changes to be legal and the side universe is built, it is time to migrate from the old to the mentioned new universe. This is done by traversing the heap and performing a specialized GC operation. As this GC is able to change the memory layout and will swap old class pointers to the new ones. Instances of classes which have added a field will have those fields populated with the JVM defaults, which are 0, null, and false. Those defaults might be configurable from within IntelliJ in a stable version of Compose hot reload. The entire machinery of the DCEVM boils down to calling a single method called redefine classes, where an array of class definitions of the changed classes is passed. Let's apply this to our counter application. While we can see the green flash indicating a successful reload, commenting out the click me text seemingly does not show any effect. Even commenting out the entire content of the button only shows effect after clicking it. Especially weird, the button content should be empty and there's still a number displayed with a bouncing effect. I'm curious if somebody at this point is already able to guess what's going on. Swapping code and migrating objects is only half of what is needed for implementing hot reload. You see, building UIs is inherently state heavy. The Compose framework makes storing and changing state so easy that some parts of it might not be visible. For example, lambdas, such as the content of the button in our demo, might be memoized by Compose to reduce unnecessary allocations. Compose uses what is called a slots table to store state. When changing code, we can tell this slots table to invalidate the state of a certain group. Groups are associated with regions of source code. Usually we can assume that one function will have one group and one corresponding group key. Larger functions, especially with control flow, might even have nested subgroups. But which groups are to be invalidated and where would we get the keys from? After recompilation, we might know which class files have changed, but how do we get the Compose groups? And after which principle shall groups be invalidated in the first place? On one hand, we want to keep as much state as possible, whilst invalidating as little as necessary. However, the cost of keeping wrong state is more expensive than over-cautionary resetting a composable which could have kept its state. Again, think of the frustrating debugging sessions which was performed on entirely wrong assumptions. We started with keep all state unless we have a good reason for invalidation, but quickly switched to invalidate all state unless we have a good reason for keeping it. We still try to aggressively find such reasons. How is the runtime able to reason about composable groups in the first place? The answer lies in the bytecode analysis module. Let's assume we have a simple app with just 3 classes: foo, bar, and app. The bytecode analysis will hook straight into the JVM. Before a class is loaded by the runtime, the actual bytecode will be analyzed. Bytecode instructions of methods therefore will be fed into Alexa, which emits compose-aware bytecode tokens, such as start restart group or end restart group. These tokens will then be passed into a tree of scopes, respecting the control flow of the method. This example here even shows that a certain scope might depend on another method, in this case padding. Note that the runtime will assign a hash value to each scope. Any significant change in the semantics of the code will result in a change in this hash value. All parsed scopes will be tracked by the runtime tracker, keeping all information about the current runtime. As an example, let's change the code of the padding function. The sample shows the composable scope reacting, showing change padding value. The modified app class will be fed into the bytecode analysis again, producing a runtime info tick similar to the DCEVM's side universe. The final step will be resolving the group keys which are due for invalidation. The runtime trees will therefore calculate another integer value called the invalidation key. This invalidation key will also include the hash value of all transitive dependencies. Therefore, the most inner scope, depending on the padding function, will resolve this key by calculating a checksum from the padding function as well as including its own hash as well. Since the padding function was changed, the new invalidation key for it changed as well. Incorporating this into the scope's key results into a changed key as well. Since the other scopes did not change, we found the only scope which needs to be invalidated. There are many more interesting problems that had to be solved for Compose Hot Reload. For example, how Hot Reload handles changed static fields, or issues about the stability of Compose group keys emitted by the Compose compiler. The biggest headaches, however, resulted by taming lambdas, lambda instances, and trying to actually understand and work with the INDI invoke dynamic instruction. The project is now stabilizing for the JVM. It is expected to have the first Kotlin and Compose compilables, including all fixes for hot reload, being available with Kotlin 2.1.20 beta 2, which is coming soon. I want to especially thank Andrei Shikov from the Compose team for all the help, and thanks to all early adopters providing feedback regularly. That's it, and as always, have fun with Kotlin.